Hi, welcome back. This is Professor Ridge and today's lesson on 5.6 Applications and Models. We do growth and decay and compound interest. Alright, so population growth. We can use the formula. It's an exponential function, p sub 0 e to the rt, or you can read that as p naught. P sub 0 or p naught, whichever way you want to read it. That's going to be your initial population. That's population when time equals 0. That's why we use the sub-zero. So that's our initial population. R is your growth rate. And T is time. And then just make note that R and T have to be in the same units. They have to match. So if R is 7% per week, T is the number of weeks. Okay, so they have to match the units. If it's 7% per day, T has to be number of days. And just to want you to recall, if R is greater than 0, that's growth. Now the book distinguishes, instead of using R in this formula, they use K. And K is always a positive number. So what they do is they write two different formulas, one for growth, one for decay. I think of them, it's the same formula, and I know if R is positive, that's going to give me growth, and if R is negative, that's going to give me decay. It'll look like this. So, you just have to make some slight modifications to the way the book presents it, but hopefully it'll make sense in a minute. Okay, so under ideal conditions, a population of rabbits has an exponential growth rate of 11.7% per day. Consider initial population of 100 rabbits. Find the exponential growth function. So what we're going to do is, R is 11.7%, so we're just going to use the formula above. The initial population is 100. E to the R. R is 11.7%, so write it as a decimal. Move it two places to the right. T. So that's all we do for that one. So what will the population be after 7 days, 2 weeks, and 150 days? So we want to know 7 days, that's what's population when T equals 7. So you just punch this into your calculator. Now be careful. You have to make sure you use parentheses, 0.117 times 7, or work that out. And again, you don't want to drop any decimal places. So you can punch that in your calculator, and we're going to round it to the nearest whole bunny. So that'll be 227 bunnies. 2 weeks. Now remember, 2 weeks is 14 days. So 100 e to the 0.117 times 14. Now it's exponential function, so this is not going to double. This is going to go more than double. So we punch that in our calculator. 100 times e to the point, you got to use parentheses, 0.117 times 14, close parentheses. And you should get 5, round to the nearest bunny. So 514. Now this one's going to blow your mind here. Again, this is exponential growth, so it starts taking off. So 0.117 times 150 days, so in about 3 months, you're going to get, so you punch that in. And what I do is if you have the calculator where you put the number first, then you hit the function button, I do the 0.117 times 150, hit equals, and that's 17.55. Then I hit my second ln button, that's the E. So, and then I times that by 100, so I kind of go backwards. So that's going to give me 4, what is that, 4 million billion, 4,186 664,475. So 4,186,664,475. So again, this is ideal conditions, right? So there's plenty of food, there's no predators. So obviously you're not going to get that ideal conditions, up to a point you will. All right, and C, find the doubling time. So again, well, I haven't told you yet. Doubling time is the amount of time for the population to double. So basically you want to find T when P of T equals twice the initial population. Okay? So you're going to plug in 2P sub 0 equals P sub 0 e to the 0.117t. Now it doesn't matter what our initial population is, because when you divide both sides by the initial population to get the exponential by itself, it cancels. So it always boils down to this formula, 2e to rt. And then you're going to do ln of both sides, so ln of 2. The ln and e cancel each other, so you get 0.117t. And then you're going to divide by 0.117. So t is equal to 5.9 days. So every almost 6 days, your bunnies are going to double if you have them in ideal conditions. Okay, let's solve that doubling time in general. So again, every time you're going to, the P sub 0 is going to cancel out. So you get 2 equals e to the rt. And you can put ln in front of both sides. Ln and e cancel, so you get rt. And then if you're solving for t equals ln 2 divided by r. Okay, so we're going to use that formula for doubling time. So you can memorize it, or you can work it out like we did for each specific problem. Alright, now let's go on to compound interest. So this should be review, but anyway, here it is. So if we have compound interest formula, A of t equals P to the times 1 plus R over N to the NT. Of course, P is principal, or the original amount, or initial amount. R is your interest rate, and typically we give it in years. N is the number of compounding periods per year. And T is the time in years. So we're going to, the R divided by N, and then the NT, what we're doing is we're scaling that interest rate so they're in the same. If we're talking about compounded daily, we want it to be in the power to be the number of days, and the interest rate needs to be converted to per day. Alright, so we have that formula. Now what we're going to do is, what if we let n get really large, and instead of doing it every day, every hour, every second, and then just do it where continuously, so n would become infinity. So we call that compounding continuously. And what that gets us is this formula, and it turns out it's just the same formula that we did for exponential growth. So it's P e to the RT, or if you want to use the P sub 0 notation, you can use that too. So either one, I tend to use the A of t, the amount, but either one, the same formula. Okay, so let's complete this table. So for A, we have an initial investment of $35,000. Interest rate is 3.2%. We want to find doubling time. So if you recall, up there at the top, the doubling time, we say T equals ln of 2 divided by the rate. So we're going to get ln of 2 divided by 0.032. Punch that in your calculator, and you should get 21.7. Okay, now we're going to do A of 5. A of 5 is going to be initial amounts 35,000, e to the 0.032, is I gotta write 32 times 5. Punch that in your calculator, and you should get 41,072.88. So 41,072.88. All right, B. Hi, welcome back. This is Professor Ridge. All right, so B, we got 5,000 as our initial investment. We want to find out the interest rate and the amount after 5 years. And then we also want to find out, so we need to figure out, we're going to use A of T equals the initial amount, 5,000, and e to the RT, we don't know R. So we know A of 5 is 7,130.90, and that's when T equals 5. So we got to solve this. So we're going to divide by 5,000 because we want to get the exponential by itself. So we get e to the 5r equals whatever that number is. I'm going to leave it in my, I'm just going to write it like this. And now I'm going to do ln on both sides. And then divide both sides by 5. So R equals, R is about 0.071. So we'll put 0.071, so that's 7.1%. And then using our doubling time, T equals ln 2 over 0.071, which is going to be about 9.8 years. Okay, so now let's try C. C is, we're given interest rate is 5.6. So A of T, P-E-R-T, we're going to put 5.6, and the amount after 5 years is 9,923.47. P we don't know, but we know R is 0.056 and time is 5 years. So you're going to now this is just a number. You just punch that in your calculator. So you're just going to divide that out of both sides. In fact, it is, and then 5 times 0.056 is 0.28. So P equals 9923.47 divided by e to the 0.28. punch that in your calculator, and you should get 7,500. Okay, and then we can figure out the doubling time. T equals ln of 2 divided by r. So we could have done this one in any order because we already knew what r was. It's 0.056, and that's going to give us 12.4. Is that correct? 12.4. Alright, and then the last one, letter D. We're given doubling times 11 years, so let's start with that. T equals ln 2 divided by r. So 11 equals ln of 2 over r. We're going to cross multiply, or multiply both sides by r. And then divide by 11. So r equals 0.063. So that's 6.3%. And then we can find out our initial investment. A of t equals PE to the RT. We know after 5 years we got 17,539.32. P we don't know. E to the R 0.063, and T is 5. So just like we did before, we're going to divide by that E to the 0.0635. So P equals, and then you just punch that in your calculator, 12,800. 12,800. All right. Okay, so carbon-14 has a half-life of 50 years. And note, half-life it equals the time it takes for half the original amount to decay. Okay, half the original amount of carbon-14 actually to not be radioactive. Anyway, so just we can simplify it, say half of it to decay, to go away, basically. So just like we did with the doubling time, it's the same thing. We want P sub 0, so for half-life, we have the exponential growth model, or decay. Now this is where I'm going to vary from the book a little bit, because again, I don't view the formula different for growth or decay. So the book makes note that, here's the book, K is always a positive number, and P of t equals P sub 0 e to the kt, that would be growth. And then this one would be decay. And I don't make a distinction between the formula. If R is positive, it's growth. If R is negative, it's decay. So you just have to keep track of what we're talking about. So for half-life, solve P of t equals half of P sub 0. So we're going to get half P sub 0 equals P sub 0. Okay, so again, we're going to divide by the initial amount. So those cancel. Take the ln on both sides. And then, so you can have two formulas, depending on which way we're doing it. If we want to solve it for t equals ln of 1/2 over r, or if you solve it for R, R equals ln 1/2 over t. So you can do it either way, depending on what you're solving. So for this one, if carbon-14's half-life is 57 years, let's try that again. Okay, so solve for R if carbon-14's half-life is 5,750 years. So we're going to do the formula. We want R, so we're going to use the bottom one, ln 1/2. If you want to put 0.5 in your calculator, make it easier, that's the same thing. And the half-life is 5,750. And you punch that in your calculator, and you get about negative 0.00012. So now we know the rate for decay rate for carbon-14. Okay, so find how much carbon-14 is lost at 3,300 years. So we know P of 3,300 years ago. P is of 0. We don't know the amount, so we're going to give this answer as a percentage. 0.00012 times 3,300. So that's going to be equal to P0. Punch this in your calculator and you should get 0.673. So note we have 67.3% of the original amount left. So the question is how much was lost. So you're going to do 100% minus 67.3% is amount that was lost, which would be 32.7% of the original amount was lost. Okay, lead has a half-life of 22.3 years. Find its decay rate, K. And remember, K, when they talk about that way, K is a positive number. So when I do my formula, so half-life, I want to solve for R. Remember, R equals ln of 1/2 divided by T. So ln of 1/2 divided by 22.3. When I punch this in, I'm going to get a negative number because R is the growth rate, so a negative R would be the decay rate. So you just change the sign back to positive to be the K. K is going to be the opposite of R when it's decay. So let's see, ln of 0.5 divided by 22.3, we get R is about negative 0.031, so that means K is 3.1%. K being the decay rate. Alright, so now let's see. Krypton has a decay rate of 6.5% per year. Find its half-life. Okay, so we want to find the half-life. So T equals ln of 1/2 divided by R. Now remember, R is the opposite. If it is, R is negative if it's a decay rate. So it's negative 6.065. So that's going to be, you punch that in your calculator, you're going to get 10.7 years. So it has a half-life of 10.7 years. Okay, so a lake is stocked with 640 fish of a new variety. The size of the lake, the availability of food, and the number of other fish restrict the growth of that type of fish in the lake to a limiting value of 3,040. We also call that the carrying capacity. The population of fish in the lake after time t in months is given by the formula P of t equals 30 or 3040 all over 1 plus 3.75 to the negative 0.32. So find population after 0 months. Okay, so remember that should be our initial. So we're going to put in 0. So that's going to be 3040 divided by 1 plus 3.75 to the 0 is just 1. I wrote the formula wrong because that wasn't going to come out E. I need an E there. So that's going to be 3.75 times 1, which is 3040 divided by 4.75. And that should give you the initial amount, which was 640. So let's see if that works. 3040 divided by 4.75 is 640, like we expected. Okay, if we do P of 5, 3040, 1 plus 3.75 to the negative 0.32 times 5. And we're going to punch that in your calculator, round it to the nearest fish, and you should get 1730. P of 10, 3040 over 1 plus 3.75. Oops, I forgot the E. E to the negative 0.32 times 10. So it's 3.2. Now, the way I would do this, if I have a calculator where I put the number first, then the E, I actually start on the bottom, and I go the E to the negative 3.2, so I go 3.2 negative, then I hit my second LN button, and I get 0.0407, then I hit times the 3.75 plus 1, and I get 1.152858265. That's my bottom number. Now I'm going to do 3040 divided by that. And if you have this button that's 1, you can just leave that number in your calculator. If you have the 1 over x button on your calculator, you hit that, and that actually moves the 1.1528 to the bottom, and you get 0.8674, and then you hit times 3040. This time I wish I had a video on me so I could show you. But anyway, you should get 2637 if you round it to the nearest fish. Okay, so again, you want to carry as many digits as decimal places you can, so you don't get too much rounding error. So when you do that bottom number, if you can leave it in your calculator, it's best. And you hit that 1 over x button, and it makes it go to the bottom, basically. So for instance, if I wanted to do 8 divided by 12, if I put 12 in my calculator first, and I hit 1 over x, that gives me 0.0833. So in essence, that's any number divided by, or 1 divided by 12 would be 0.08333 forever. And then I hit times 8, and I would get 0.66666. So that's the same thing as doing 8 divided by 12, and you get 0.66666. All right. So anyway, that's a great button if you can learn to use it. P of 20, I'm not going to write this one down, I'll just tell you the answer. So you should punch it in your calculator and you should get 3021. And you see it's not going to grow much faster than that because we're limiting values 30, 40. So, you know, if we put in 100 months, we're going to get maybe a little bit closer to 30, 40. But it's going to pretty much stable out right around this number. Okay, so that concludes the lesson for 5.6. Go to My Math Lab, complete your exercise there, and I'll see you next time.